Everyone, I'm Shreya Bondili, and today I'll be speaking about smarter Achiral HPLC method development through leveraging in-silico tools for efficiency. First, I'll quickly introduce Pharmaron, who we are and what we do. Then I'll cover some background on the stages of HPLC method development and how in-silico tools can be used to make this process more efficient. I'll also touch on our in-house in-silico incorporated workflow, along with a quick case study example to illustrate how it looks in practice. And finally, I'll finish off with some of the benefits we have found with in-silico tools and some considerations for their use. So Pharmaron, who are we? We are a leading contract research organization who offer a range of services in the life sciences sector, supporting clients from across the world, from small biotechs to top pharmaceutical companies. We have over 21,000 employees working in 23 different sites located in America, UK, and China. I work at our Hoddesdon site, which is situated in the UK. At Hoddesdon, we offer a wide range of services spanning the whole drug discovery and development process. Within our analytical chemistry team, we have over 100 employees across drug substance and drug product. I currently work as a scientist in drug substance, primarily focusing on early phase development projects for small molecule APIs. But my journey at Pharmaron actually started in 2023 as a placement student, and as part of my MChem degree, I carried out a master's project which involved the integration of ACDLabs into our departmental workflow. So Pharmaron had acquired the license for the method selection suite at the start of my placement, and my work involved establishing guidance for using in-silico tools for HPLC method development. And that's exactly what I'm here to talk to you guys about today. So typical HPLC method development starts with setting the analytical target profile. In this, the desired method criteria are specified, so for example, sensitivity and precision, and the ATP helps define when a method has been developed. ATP and any other known properties of the analyte can guide the selection of an appropriate HPLC technique. Then typically a variety of columns and mobile phases are screened to identify the most suitable combination that gives reasonable separation of your analytes. Once these initial conditions are chosen, critical method parameters affecting separation such as pH or temperature are systematically optimized to enhance that separation a bit more. Then finally, the developed method is validated to establish its performance and demonstrate that it's suitable for its intended purpose. Historically, this process involves extensive manual experimentation, especially during the optimization stage, where typically a one factor at a time approach is taken. So it can be a time-consuming and resource-intensive process which relies heavily on the experience of the chromatographer. In-silico tools can be leveraged to streamline this process. So today I'll be focusing on physicochemical predictions and chromatographic modeling. Physicochemical predictions can help guide selection of an appropriate technique and suitable screening columns or mobile phases. This allows for a more targeted screening approach, which increases the likelihood of finding a suitable combination the first time around. Chromatographic modeling allows multivariable optimizations, which minimizes the number of experiments required. So let's have a look at exactly how these tools can be used. Two physicochemical predictions that can be used for HPLC method development are log-D and pKa. Log-D is the pH-dependent measure of hydrophobicity, and it's given by this equation here, where X is a given analyte. It essentially describes the partitioning of a compound between octanol and water. So a high log-D value indicates high hydrophobicity. In reverse phase chromatography, retention is primarily driven by the hydrophobic interactions of your analyte with the apolar stationary phase. So for good retention in reverse phase, you ideally want your compound to have a high log-D. This makes log-D a valuable tool for selecting an appropriate chromatographic technique, and it avoids screening stationary phases that might not yield desired results. For example, if a log-D curve of a compound is low across all pHs, like this one, then this might indicate poor retention in reverse phase. So this might prompt considerations of alternative techniques that might be more suited to polar compounds, such as hydrophilic interaction chromatography. Log-D curves can also be used to identify a suitable mobile phase pH that would maximize hydrophobicity. pKa values can guide mobile phase pH selection as well. To maximize hydrophobic interactions, it is ideal for the compound to be in its neutral form. pKa values can indicate pHs at which the compound exists in its neutral form. For example, ascorbic acid has a pKa of 4.2. So at pH 4.2, it exists 50% in its neutral form and 50% in its ionized deprotonated form. And as a general rule of thumb, 2 pH units away from your compound, from the pKa value of your compound, indicates that the compound exists almost entirely in its neutral form or ionized form, depending on which way you go. So in this case, at pH 2.2 or below, ascorbic acid exists almost entirely in its neutral form. So if you were trying to analyze ascorbic acid by reverse phase chromatography, then you would go for a pH that is below 2.2 in order to maximize its retention. Unfortunately, it's not always as straightforward as that simple example. Sometimes you might have multiple ionizable groups that may make it difficult to pick a pH where your compound is neutral. For example, amoxicillin has both acidic and basic functionalities, and this results in the compound not existing in a neutral state across the whole pH range. But even in cases like this, pKa predictions can still be very useful. If your molecule exists in multiple protonation states, during reverse phase analysis, this can lead to poor peak symmetry. And pKa predictions can be used to minimize this by selecting a pH where your compound exists in a single dominant protonation state. So in this example of amoxicillin, you might go for a pH of 5 to 6 because at this pH, amoxicillin exists in protonation state 2, which is where the acid is deprotonated and the base is protonated. Physicochemical predictions also help build method robustness into the method right from the start, because you can use them to choose pHs where small fluctuations don't significantly affect the ionization of the compound, and so consequently doesn't significantly affect their chromatographic behavior. Moving on to chromatographic modeling. First, one must identify the parameters that need to be optimized. Then some initial modeling experiments need to be run where those chosen parameters are systematically varied. So for example, if I wanted to build a temperature and gradient model, then I would run different temperatures, each at different gradients for the initial experiments. From these runs, the retention data, such as retention times, peak areas, peak widths, are all collected and fed into the modeling software. The software then fits this data to retention model equations to calculate some constants. And using this fitted model, the software is then able to simulate what the chromatograms would look like under the different method conditions. So in the example that I gave, you would be able to see what the chromatogram looks like under different temperatures and different gradients. Essentially, those initial modeling experiments are like training data, and the number of initial experiments that are required depends on the linearity of the retention model equation that's being used. So if it's linear, you would only need 2. If it's non-linear, you would need at least 3. At Pharmaron, we begin the HPLC method development process by first predicting log-D and pKa using ACDLabs Perceptor. Using this information, we carry out a directed screen where we screen combinations of 2 aqueous mobile phases, 2 organic mobile phases, and 6 columns. The columns are chosen from predefined sets which are intended for specific purposes, such as polar analytes or isomers. We also have a maximum orthogonality set for when you're unsure how your compound will behave. And this set essentially has a bit of everything. It's got phenol columns, polar moiety columns, C18 columns. And we also have a column screen set which can be operated at extreme pHs, so this is ideal for analytes that require such pHs. To choose which column screen set to look at, we follow a structured flowchart which is designed to guide the choice based on your mobile phase selection and key analyte properties such as stereoisomerism or polarity. The best combination of column and mobile phases is then chosen based on separation target criteria. So typically this is resolution, tailing factor, and capacity factor. And combinations which meet these criteria are considered a hit. So once these initial conditions are chosen, if the separation requires further optimization, then we carry out chromatographic modeling in ACDLabs LC simulator. Most of the time, we typically do temperature and gradient optimizations, but sometimes we do also carry out pH. So once one or more suitable methods have been generated within the software, we then run these experimentally just to make sure that they're performing well practically. When we are carrying out a 3D optimization of pH, gradient, and temperature, we typically run 27 experiments. So these are combinations of 3 pHs, 3 temperatures, and 3 gradients. The ranges that are chosen for these are based on literature search and software recommendations. For the pH, we do 3 points, which range 1 pH unit. Typically, the midpoint is a screening pH, and then you go 0.5 pH units above or below. Depending on your buffering capacity, this might not be possible to go above or below 0.5 pH units. So in these cases, you can adjust these. For temperature, we run 3 points, which range 20 degrees. So for example, 30, 40, or 50 degrees, or 25, 35, 45, depending on your column stability. And for the gradient slope, we run 3 points at 2.5, 5, and 7.5% B per mil. If your peaks of interest are observed to be quite close eluting during the screen, which is typically done at 5%, then you might want to substitute the steeper gradient for a shallower one. This is just to ensure that the input data that you're obtaining is good enough to build a reliable model from. So the equation used to model the influence of pH on retention is nonlinear. So you need at least 3 experiments to model pH. But for temperature and gradient, they're linear, so you only need 2 as a minimum. So in theory, you could optimize pH and temperature and gradient in just 12 experiments. So this would be combinations of 3 pHs, 2 temperatures, and 2 gradients. However, to increase the accuracy of the model, we try and do 3 points for each wherever possible. So let's go through a case study to illustrate what this workflow looks like in practice. For this method, we had 3 analytes of interest: the starting material, the intermediate, and the active pharmaceutical ingredient, the API. So we generated log D and pK predictions for these. And for the pK predictions, the Perceptor software uses 2 different algorithms, so it uses GALAS and Classic. So if these were very different, we would choose one mobile phase pH based on each prediction. But in this case, they lined up pretty well. Perceptor also generates a visual graph to aid in pH selection, where the log D is plotted against pH. So the areas are highlighted in green to denote suitable pH regions, and part of how it determines the suitability is based on dominant ionic forms of the compound. So if there are multiple ionic forms predicted to exist at pH, this is shown as orange or red, depending on the percentage of the ionic forms present. So for this reason, the basic region is highlighted as green in this example, but because the compounds exist in one single ionic form. However, when you look at the log D values in this region and the pK predictions, you can see that the starting material and the API exist almost entirely in the ionized state. So to maximize our retention, the acidic pH, where the compounds are in their neutral state, would be more appropriate. So that's exactly what we did. We screened 2 acidic mobile phases, 0.1% phosphoric acid in water, which is around pH 2, and ammonium formate in water at pH adjusted to 3. For the organic mobile phases, we went with acetonitrile and methanol. And for the column screen set, we followed our flowchart and it suggested to screen the maximum orthogonality group. So once we did the screen, we identified our best hit based on our separation target criteria, and the hit we decided to take forward was a centers expressed C18 column with phosphoric acid and acetonitrile as the organic, aqueous and organic mobile phases. So we often get multiple hits within a screen. So in such cases where all our initial separation target criteria are being met, we consider other factors to help choose which hit to take forward. So these factors might include baseline noise or ease of mobile phase prep. In this case, we actually got a good hit with ammonium formate on the same column. However, we preferred phosphoric acid as it had a more stable baseline. For this hit, our separation looked great. All the peaks were well resolved, as you can see in this chromatogram. So we then carried out crude forced egg studies, and we observed 3 new impurities. Unfortunately, one of these impurities was eluting very close to the API right on the tail. And even though it had a resolution of 2.1, it was not baseline resolved, as you can see here. So to improve the separation, we decided to optimize the temperature and gradient using chromatographic modeling. So we carried out 9 experiments, 3 temperatures, 30, 40, and 50 degrees, each at 3 different gradients, 2.5, 5, and 7.5% B per mil. We then fed the retention data collected from those 9 experiments into ACDLabs LC simulator. So this is what the interface looks like. You can easily edit the gradient and temperature in the left-hand side here. And the minimum resolution, which corresponds to the resolution between your critical pairs, so this is your 2 closest eluting peaks. And on the right-hand side, you can see your gradient editor and resolution map. So the gradient editor gives you a visual representation of the chosen gradient, and you can edit the gradient using this as well. The resolution map is a heat map showing the effect of method conditions on the resolution of the critical pair. So the blue corresponds to low resolution and the orange corresponds to high resolution. And these diagonal black lines are indicating that the predefined suitability criteria are not being met. So in this case, it was a resolution of 1.5 that wasn't being met. These resolution maps can also be used to get a predicted sensor method robustness, as you can easily see the influence of small fluctuations in the method conditions on the chromatography. From this resolution map, where the temperature is on the y-axis, we can see that a lower temperature gives slightly higher resolution. So we ended up going with a low temperature of 30 degrees, both for the higher resolution and also sustainability and column longevity. So this is what our final method looked like experimentally. So the experimental is in black and the predicted is in red. The prediction accuracy that we got was pretty good. We got an average error of 0.8% and an absolute error of 0.1 minute. And the resolution that we got between the API and the impurity was far better. We got a resolution of 4.5 compared to the previous 2.1. And this method has now been validated and it's being used as a stability indicating method. So to finish off, I just wanted to note some of the benefits that we've observed with this in-silico approach and some considerations that we would recommend as well. With the ever-growing need for sustainability, the consumption of solvents and subsequent waste that's generated by HPLC method development needs to be reduced. And in-silico tools are a great way of doing that. In-silico tools also allow you to build in robustness early on into your methods and save you a lot of time further on down the line. Modeling also allows you to make informed prompt decisions. So for example, we've had cases where we build a model and after looking through different method conditions in LC Simulator, we realized that we can't get our desired separation under the current design space. So we ended up changing mobile phase or changing column to get our desired separation. And these kind of decisions can take much longer to arrive at with manual optimization, and you're wasting resources along the way as well. The great thing about chromatographic modeling is that once you've built a model, you can always revisit it, either to add more compounds or maybe redevelop a method for a different purpose. This in-silico approach also simplifies method development and minimizes the reliance on the chromatographer's experience, so it makes method development more accessible as well. One of the things to consider is that prediction accuracies don't always correspond to method viability. So we've had average errors of more than 3.5%, but the software optimized method is still viable because the resolution was still sufficient. However, if you have quite close eluting impurities, then even small inaccuracies could be detrimental to your resolution. As with all predictions, these should be treated as preliminary, and it should always be tested experimentally to make sure that they're performing well in practice. Reliable modeling requires reliable input data. If you give it rubbish in, it's going to give you rubbish out. So for example, if you give it non-representative data by running on a bad degrading column, then you're not going to get representative predictions. And finally, mass spec can be really useful for peak tracking, especially in complex mixtures where elution orders might be significantly impacted by the assessed method conditions. Thank you everyone for listening, and are there any questions?